Alright, let's start. A-class flares. The sun is never truly quiet. Even during solar minimum, the most inactive phase of the sun's 11-year cycle, the solar surface crackles with small-scale electromagnetic activity. The weakest measurable flares are classified as A-class, defined as events producing a peak X-ray flux of less than 10 to the power of -7 watts per square meter at Earth's distance. They are so faint that their X-ray output is comparable to background solar radiation and detectable only with sensitive satellite instruments. An A1 flare is the baseline. Every step up in number within the class, a 1 to A9, represents a doubling of energy output. Despite their modesty, A-class flares are not trivial to the science of solar physics. They occur constantly, and their study reveals the mechanisms of magnetic reconnection, the process by which twisted magnetic field lines in the solar corona snap into new configurations and convert magnetic energy into heat, radiation, and particle motion. Understanding A-class flares is understanding the fundamental engine that powers all flares at every intensity level. They are the sun breathing quietly, a perpetual whisper of electromagnetic activity that never entirely ceases. B-class flares. One step above the A-class baseline, B-class flares represent a tenfold increase in X-ray flux, from below 10 to the -7 up to 10 to the -6 watts per square meter at Earth's orbit. They remain too faint to cause any detectable effects on Earth's environment. The planet's magnetic field and atmosphere absorb and deflect the modest increase in X-ray radiation without any measurable consequence at the surface. B-class flares occur frequently during periods of low solar activity and are observed by satellites monitoring the sun in soft X-ray wavelengths. Their value to solar physicists lies in what they reveal about active regions, patches on the solar surface where strong magnetic fields have erupted through the photosphere, creating sunspot groups that are the breeding grounds for all larger flares. When an active region produces persistent B-class flaring, it signals that the magnetic complexity of that region is rising, and that conditions may be building toward more energetic events. B-class flares are the sun warming up, background noise against which solar physicists read the shifting tension of the solar magnetic field, watching for the indicators that will precede something more significant. C-class flares. C-class flares are the first category of solar flare with any measurable, if minor, effect on the near-Earth environment. They represent another tenfold increase in X-ray flux over B-class events, reaching peak outputs between 10 to the -6 and 10 to the -5 watts per square meter. At these energies, the enhanced X-ray emission slightly increases the ionization of Earth's upper atmosphere, the ionosphere, on the sunlit side of the planet. This can cause minor degradation in high-frequency radio communications, particularly affecting radio operators and aviators who rely on those frequency bands for long-distance transmission. The disturbance is short-lived, typically lasting minutes to tens of minutes as the flare rises and fades. C-class flares are common during active periods of the solar cycle, occurring multiple times per day near solar maximum. They do not produce geomagnetic storms and pose no threat to satellites, power infrastructure, or human health. But they represent the threshold above which a flare begins to interact meaningfully with Earth's electromagnetic environment. The first rung of the ladder where solar activity transitions from purely astronomical observation to something that touches human technology. M-class flares. M-class flares are moderately strong events, 10 times more energetic than the largest C-class flares, with X-ray flux between 10 to the -5 and 10 to the -4 watts per square meter. They are capable of causing significant effects on Earth. Radio blackouts on the sunlit side of the planet during M-class events can interrupt shortwave communications for up to an hour, disrupting aviation, maritime operations, and emergency services that rely on high-frequency radio. Enhanced particle radiation from M-class flares elevates exposure levels for astronauts aboard the International Space Station and for passengers on high-altitude polar flights where Earth's magnetic field provides less shielding. Larger M-class events, particularly those in the M5 to M9 range, can trigger minor to moderate geomagnetic storms if accompanied by a coronal mass ejection, a separate but often associated expulsion of solar plasma. These storms can produce visible auroral displays at mid-latitudes, temporarily distort compass readings, and introduce noise into power grid systems. M-class flares occur multiple times per month near solar maximum and serve as the workhorse events for space weather forecasters, common enough to provide regular data but energetic enough to require monitoring and response across multiple industries. X-class flares. X-class flares are the most powerful events in the standard solar flare classification system, with X-ray flux exceeding 10 to the negative 4 watts per square meter at Earth's distance. Every whole number step in X-class magnitude, X1, X2, X3, represents a further increase in intensity, and the scale has no defined upper limit within the class. X1 flares cause strong radio blackouts on the entire sunlit hemisphere of Earth, disrupt satellite navigation signals, and can produce radiation storms that force astronauts into shielded areas of the space station. X-class flares that occur in active regions positioned toward Earth produce the most severe near-Earth effects, particularly when accompanied by fast coronal mass ejections. The largest X-class events can temporarily alter the drag on satellites in low Earth orbit by heating and expanding the upper atmosphere, causing unexpected orbital decay that requires ground controllers to perform corrective maneuvers. X-class flares also produce solar energetic particle events, streams of high-energy protons accelerated to a significant fraction of the speed of light, that arrive at Earth within minutes to hours of the flare and can damage unshielded electronics. They are the events that transition space weather from inconvenience to genuine infrastructure risk. X10 plus extreme flares. The X-class scale is open-ended, and some historical events have dramatically exceeded what the standard numbering implies. On November 4, 2003, the Sun produced a flare so intense that it saturated the X-ray detectors aboard the GOES satellite instruments used to classify flares. The measurement system went off-scale. Subsequent analysis estimated the event's true peak intensity at approximately X28 to X45, making it the most powerful flare directly recorded with modern instruments. At these energy levels, radio blackouts affect the sunlit hemisphere for hours rather than minutes. The enhanced X-ray flux heats the upper atmosphere enough to measurably increase drag on low-orbit satellites. If a solar energetic particle event accompanies the flare, the particle environment near Earth becomes hostile to unshielded electronics and biological tissue in a matter of minutes before any protective orbital maneuver is possible. Extreme X-class flares represent a category where the standard scale becomes qualitative rather than quantitative. A regime where the question shifts from how much will communications be disrupted to which systems will fail and for how long. They serve as proof that the sun's dynamic range extends significantly beyond what most infrastructure was designed to tolerate. Coronal mass ejection. A coronal mass ejection is not a flare. It is a separate event that often accompanies one, and it is frequently more consequential. Where a flare releases energy primarily as electromagnetic radiation, a coronal mass ejection expels a cloud of magnetized plasma from the sun's corona. Billions of tons of charged particles traveling at speeds between 300 and over 3,000 kilometers per second. When a fast Earth-directed coronal mass ejection arrives at our planet, typically 1 to 3 days after the associated flare, it compresses and distorts Earth's magnetic field in what is called a geomagnetic storm. The most severe storms can induce electrical currents in long conductors on the ground, power lines, pipelines, railway tracks, strong enough to trip circuit breakers, damage transformers, and in extreme cases cause widespread power outages that last not hours but weeks or months, as large transformers are difficult to replace quickly. A geomagnetic storm, rated G5, the highest on the current scale, can produce auroras visible at tropical latitudes and degrade GPS accuracy globally. The storm also elevates radiation exposure for aviation and human spaceflight. Coronal mass ejections are the mechanism by which solar events translate most directly into tangible effects on modern civilization, and they are the primary reason space weather forecasting exists as a dedicated scientific and governmental function. Solar energetic particle event. When a large flare or fast coronal mass ejection drives a shockwave through the solar corona and interplanetary space, that shockwave can accelerate protons and heavier ions to velocities approaching a significant fraction of the speed of light. The resulting stream of high-energy particles, called a solar energetic particle event, or SEP, can travel from the Sun to Earth in as little as 8 minutes for the most energetic protons. giving almost no warning time between the flare and particle arrival. At these energies, protons penetrate satellite electronics and can cause single-event upsets, bit flips in memory and logic circuits that corrupt data or cause systems to behave unexpectedly. In severe events, cumulative radiation damage degrades solar panels and detector arrays permanently. For unshielded astronauts in deep space and beyond the protection of Earth's magnetosphere, a major SEP event can deliver a radiation dose that approaches or exceeds occupational lifetime limits within hours. The 1972 Solar Energetic Particle event, occurring between the Apollo 16 and Apollo 17 missions, was estimated to have been large enough that, had astronauts been on the lunar surface at the time, they could have received a life-threatening dose of radiation. SEP events are the fastest-acting hazard in space weather, demanding automated detection and pre-positioned shielding strategies rather than reactive responses. Carrington's class event. On September 1st and 2nd, 1859, British astronomer Richard Carrington observed an intense white light solar flare, the first ever recorded, and within 17 hours, a coronal mass ejection arrived at Earth with a speed unprecedented in the observational record. The geomagnetic storm that followed, now called the Carrington event, was the most powerful in recorded history. Telegraph systems across North America and Europe failed catastrophically, with some operators receiving electrical shocks from their equipment and telegraph paper igniting from induced currents. Auroras were visible at tropical latitudes, reported as far south as Cuba, the Bahamas, and Hawaii. The storm's intensity on modern scales is estimated at G5+, beyond the maximum of the current classification system. If a Carrington equivalent event struck today, the consequences for modern infrastructure would be orders of magnitude more severe than in 1859, because civilization now depends on interconnected electrical grids, satellite networks, and communication systems with far less tolerance for geomagnetic disturbance than Victorian telegraph lines. Studies commissioned by national governments and insurance institutions have estimated damage to global infrastructure in the trillions of dollars and recovery times measured in years, not days. The Carrington event is not a historical curiosity. It is a demonstration that the sun is capable of producing events that modern society is not adequately prepared to absorb. Superflare. Most research on stellar flares focuses on our own sun, but observations of other sun-like stars by space-based photometry missions have revealed something that challenges assumptions about solar behavior: superflares. A superflare is a flare 10 to 10,000 times more energetic than the largest flare ever recorded from our sun, occurring on stars that are otherwise similar in mass, temperature, and age. Studies of thousands of sun-like stars have found that superflares occur with a frequency of roughly once every few thousand years on any given star, suggesting that our own sun may be capable of producing such an event, even if none has occurred in recorded history. A solar superflare at the lower end of the observed range would produce electromagnetic and particle effects orders of magnitude beyond the Carrington event. At the higher end of the distribution, the X-ray flux alone could strip significant portions of a planetary atmosphere over the course of the event. The scientific debate around whether our sun can genuinely produce such events, or whether subtle differences between active and quiet sun-like stars make it statistically improbable, remains open. If the sun is capable of superflares, then the Carrington event is not the upper bound of solar behavior, but merely the largest event within a short observational window. The sun's past and future may both contain entries that our instruments have never been asked to record. Every flare, from the faintest A-class whisper to the theoretical superflare, originates in the same process: magnetic field lines snapping under the pressure of their own complexity, releasing energy stored invisibly in the solar corona. The sun does not intend any of this. It has no awareness of the networks and satellites and biological tissue that its releases affect. It simply runs the mathematics of plasma physics at a scale that dwarfs everything humanity has built, and occasionally the arithmetic produces results that cross the distance between stars and still carry enough energy to matter. That distance, 8 light minutes, is all that separates every device on Earth from a star that is, on average, perfectly stable. If you want to see more, click the video on screen now.